that it wasn't clear to me why you didn't get going up 2 phonon modes or down 2 phonon modes. And the answer is simple, actually. It's just the detuning again, right? Because in order to go up 2 phonon modes, you need to, say, absorb 2 photons of the same color, right? 2 red ones or 2 blue ones if to go down. And that means that you get kind of they're both detuned by this in the same direction then. Whereas if you have this from going from state of the ground to the excited state. Whereas if you have 1 blue photon and 1 red photon, the detunings cancel and it works out. Similarly, if you're going from EG to GE, you need 2 photons of the same kind, add 1 and subtract 1. And if you have a red one and a blue one, then the detunings are now, one is plus and one is minus. So it is off. OK? So are there other questions about what we've been doing so far? Yep.
So about the complexity classes, the NP. So is it the idea that the NP problems in P are much harder than the ones in P?
Well, not necessarily. So well, let me discuss that a little bit today. But so yeah, let me review first of all what P and NP are. So P, remember, roughly speaking, is the class of languages. OK, I guess it's not going to be roughly speaking. Decidable in polynomial time on a classical computer. And I'm adding that caveat because today we're going to throw in a quantum complexity class. And then NP, and this will be a rough definition, is the class of languages checkable in polynomial time. And so to answer your question, P is obviously included in NP, right? Because if you can actually just answer the question, you don't need the witness at all to check it. So there are certainly problems in NP which are easy, right? Because they're also in P. But there's a strong belief that P is not equal to NP. That's one of this kind of most famous open problems in computer science, and it's a huge problem that will probably remain open for a while. No one has a strong idea of how to solve it. And if that's the case, then there are some problems in NP which are not in P and therefore are, in fact, hard, which require super polynomial and probably exponential time. Yeah? So
if you could find one problem which was in NP and not in P, we would have proved the conjecture.
Yeah, if you can prove that it's not in P.
So we don't know even of one problem that is in NP that is not.
Well, we have some very good candidates, and that's the last thing I wanted. Well, the last thing that I didn't have time to do yesterday that I'm going to start with today. But are there other questions about what we've been doing so far? OK. So yeah, so this P versus NP problem, big open question. How could you hope to prove that P is not equal to NP? Well, one approach would be to say, OK, let's find some problem that we think is in NP and not in P, and then somehow prove that there's no polynomial time algorithm to do that. But as I kind of mentioned a couple of times yesterday, that's not clear how you could do that, right? How do you really show that there's no polynomial time algorithm for doing something? But there is a kind of a different approach, which is saying that, well, if you could solve this problem in polynomial time, you could do something that's unlikely to be true, unrealistic. And again, we don't have anything that kind of is a concrete way of saying, oh, it's definitely not possible. Then it wouldn't be an open question. But we can kind of show that, that solving certain problems implies quite a lot. And so the main tool for doing that is something called a reduction. So we say that a language L reduces to the language M if there exists some polytime computable function which maps bit strings to bit strings, such that that x is in L if and only if f of x is in M. OK? And so what this means is that if you have an algorithm to solve the language M, to decide the language M, then that will automatically give you an algorithm, a polynomial time algorithm. If the original one is polynomial time, this will give you a polynomial time algorithm to decide the language L. Why is that? Well, if somebody gives you an instance of L, x, and says, is this an L or not? Well, what can you do? You can say, oh, well, let me compute f of x. And then I have this algorithm to decide whether f of x is in M or not. And if it's in M, then by this property, I know that x must have been an L. And if f of x is not in M, then again, applying this, I know that x is not in L. OK? So that means that M is in some sense harder than L, or at least as hard as L, right? Because if you can solve M, you can also solve L. But the reduction doesn't have to be both ways. So it could be that L is strictly easier than M, that there's some algorithm that solves L, that decides L without deciding M. OK? But in some cases, there can be reductions in both ways. OK? Does that make sense? And then we say that a language M, and let's say that M is in NP. This language is NP complete if for all L in NP, L reduces to M. OK? So this means that a problem M that's language M that's NP complete is harder than any language, at least as hard as any other language in NP. And in particular, if there's a polynomial time algorithm for an NP complete language, then there's a polynomial time algorithm for any language in NP, which would imply that P is equal to NP. OK? So this question of can we find some language that's in NP but not in P becomes, well, just take any NP complete language. And there's many, many, many known. I don't know, hundreds or something. And if you can only show that that particular problem is outside P, then you're done, of course, because you have to. But moreover, if you can find the polynomial time algorithm for that problem, then you know that P is actually equal to NP. So you're done in either direction if you can only resolve the question for this one particular language. And kind of the standard example of an NP-complete language, and the one I showed you yesterday, I described the k-sat problem, right? You have a Boolean formula with k variables per clause. And that problem is NP-complete for k greater than or equal to 3. So k equals 2. 2-sat actually has a polynomial time algorithm, but 3-sat is NP-complete. This is called the Cook-Levin theorem. Yeah.
Sorry, it just that arrow above in the definition, is that the both ways?
This one? Yeah, if and only if.
Okay.
That's important. OK? So there are questions on this. Yeah.
So when you say the language is 0, 1, you can have any arbitrary length, right?
Yeah. So yeah, and it has to have. So if it's a finite language, so if it's a language that only has finite many bit strings, then there's automatically a polynomial time algorithm for it because you can just list all the possible things in the language, and that's just some constant. It might be a big constant, but it's a constant, and so that's straightforward.
Right. Okay. Yeah. That answers the question.
Yeah. Any other questions? Yeah, so just following up that, all of this stuff about complexity theory, it's only really well defined and only really meaningful in the asymptotic limit, where you imagine kind of arbitrarily large things. And it's not, and I don't mean sufficiently large, I mean arbitrarily large, right? We're talking about the scaling as the input sizes get larger and larger, right? Is it polynomial or is it exponential? Right? For any finite size, you can always imagine some weird polynomial that will fit those points. But as the size gets arbitrarily large, then exponential becomes meaningful. Right, OK. So this is all I'm going to really say about classical complexity theory. I guess that's not completely true. But the next step, the next thing I want to do is introduce a quantum complexity class. Because, of course, P is the class of languages decidable on a classical computer in polynomial time. And we're interested in the class of languages that you can decide on a quantum computer in polynomial time. And hopefully, and I'll give you some examples where we think it's true, that's bigger. Right? There's some things that you can do on a quantum computer that you can't efficiently do on a classical computer. So that class, the usual version of it, is called BQP. And so the B stands for bounded, because we're going to have some bounds on the probability of success. The Q, obviously, well, I hope it's obvious, is quantum. And the P is still polynomial. So this is the set of languages for which there exists a quantum algorithm A of x I'll call it A sub L of x, I guess, in this case. So first of all, it should run in polynomial time. And the input size. And so now we have to get this bounded probability thing. So classically, we were dealing with deterministic computation, although you can define probabilistic computation as well. But quantumly, I mean, you can define deterministic computation, but it's not very natural, right? Because everything you do is going to have some probability associated with it when you make the measurement at the end. So we have to capture that in our definition here. And So that goes two ways. So one is if x is in the language, well, then we want this algorithm to accept, to say yes, with a high probability. And the number I'm going to choose for high probability is 2/3. That's the standard choice. And if it's not in the language, then it should say no with probability at least 2/3. Or conversely, say yes with probability at most 1/3. OK? So why did I pick 2/3? No reason. It's just kind of symmetrical, right? Because then you have kind of, well, yeah, OK. You kind of have, you have 1/3 that's a region of yes, 1/3 that's a region of no, and 1/3 that's a region of maybe. But really, this 2/3 is not important, right? You could have picked 4/5 or 51% or anything you like, any kind of constant number you like would be just the same. And why is it just the same? Remember, this is a complexity class, so it's a whole bunch of languages, and we can adapt the algorithm to the exact definition. So, for instance, if we had something that was say 4/9. Well, sorry, 4/9 is less than a half. So it has to be greater than a half. But really just a half plus epsilon. Any epsilon, constant epsilon is fine. Then what would we do? Well, we'd say, well, we'll take this algorithm that accepts with probability. Yeah, actually, sorry, let me go the other way. It's clear that an algorithm that does this will also accept with probability a half plus epsilon. What if it was 1 minus epsilon? So we wanted a probability that was very close to 1. Well, what we could do, we could take this algorithm that accepts with probability 2/3 and run it a whole bunch of times, right? And if we get yes more than 2/3 of the time, plus some, or 2/3, more than 2/3 minus a little bit of the time, we'd say, OK, almost certainly it's going to accept, right? And so we'll say yes. And if we run this algorithm and we get no more than about 2/3 of the time, then we're pretty sure that it really is no, right? And the probability is much higher than 2/3, right? That was the case for one time of the algorithm, one run of the algorithm to give the right answer. But to get the same right answer many, many times, right? If it was a no instance, it would be saying no about 2/3 of the time. And if we're actually getting yes about 2/3 of the time, that's really unlikely, right? And by repeating many, many times, you can make that probability as high as you want, right? So if you want accuracy epsilon, if you want to say 1 minus epsilon, you have to repeat about log 1/epsilon times before you're pretty sure. And the upshot is that actually it doesn't even have to be 1 minus a constant. It could be 1 minus 1 over some polynomial in the size of the input. And you'd still get the same complexity class. Now, if you want to be really, really careful and say it's 1 minus something that's exponentially small in the size of the input, now you're talking a different complexity class. And it may well be that there's differences between those classes. But that's insisting on a really ridiculously high probability of acceptance. So this is one of the reasons, again, why we allow polynomial factors in the definitions of these complexity classes and in complexity. Because this constant would matter if we insisted on saying, oh, it takes exactly time n squared, right? Because then repeating it to add that extra log 1/epsilon might make it longer, right? And it might not work anymore. So the advantage of allowing polynomial flexibility is we don't care about these kind of small variations in the definition of these complexity classes. OK? So there are questions about that? OK. So then one last comment about complexity. So how are these complexity? How is BQP related to P and to NP? Well, I already said that we have P and NP look something like this, with the NP complete problems here. So we believe that NP is bigger than P, but certainly P is included in NP. And what about BQP? Well, certainly BQP includes P as well, right? Because if you have a classical algorithm for a problem, you can just turn it into a reversible algorithm and run it on a quantum computer. So there's a quantum algorithm as well. But we think that BQP actually looks like this. So first of all, we think there's problems that are in BQP that are not in P. And I'll show you an example of that soon. But we also think there's problems that are BQP that are not in NP, that cannot be efficiently checked on a classical computer. And we think that there's problems in NP that are not in BQP, things like KSAT. We don't think it can be solved on a quantum computer. Now, the certainty in either of those statements is much less than the strength of the belief that P is not equal to NP. But there's still some pretty good evidence of that. And in fact, we believe that there are problems in here as well that are in BQP and in NP, but not in P. And the kind of the standard example of an algorithm, quantum algorithm, where there's no known classical algorithm is for factoring large numbers. And I'll show you that. That's Shor's algorithm, probably starting tomorrow. But factoring is a problem that's also in NP. So I'll talk about this more when I talk about factoring. OK? So anyway, this is how we believe this diagram looks. And of course, there's many more complexity classes that people have written down. Some of them very interesting and important. Some of them really weird and niche. But you can fill out a much bigger diagram if you like. And that helps kind of understand the relationships of different kinds of properties. But these are kind of the core ones that you need to know if you're thinking about quantum computing. OK? OK. So anyway, so we believe these are separate, but we have no real way of proving that. So what can we say? Well, one approach that people have used to try to separate, oops, this one didn't get erased. Maybe I'll just skip it. I don't need that many boards. So one approach that people have used in order to try to separate complexity classes, to try to prove hardness, is something called oracle problems. So an oracle is some black box that's mapping n-bit strings to bits, although it doesn't really have to be to bits. Sorry, to bits. And the idea is the oracle is just kind of given to you. You put in an input in z2 to the n, and it gives you an output. So you ask it, you ask it a question like, 537, and it says yes. And then you say 123, and it says no. OK? And you have no idea how it's working. It could have any structure inside it at all. You're not allowed to look inside the black box. But then your goal is to figure out some property of this black box. So for instance, yeah, do I want to? Yeah, OK, sure. So, so one oracle problem that we'll be talking about later this week would be saying, is there any input that we can give this oracle that will give the answer yes? Okay, and that classically that takes you kind of have to try almost all the queries before you're pretty sure. I mean, you might get lucky and find a yes very quickly, but if there's only one yes out of all the 2 to the n possible inputs, that could take a very long time. And quantumly, it still takes a long time, but you can do it faster. And that's Grover's algorithm. But OK, so what is the point of doing this? Well, what we can do is we can define the query complexity of a problem. This is called an oracle. And so let's take some property of oracles. Then we say the query complexity of this function is the minimum number of queries to the oracle needed to calculate f. Okay, and again, we're talking about complexity, so we're interested in kind of the asymptotic scaling as we think about larger and larger oracles. So obviously, for any oracle, the query complexity is going to be at most 2 to the n. Why is that obvious? Well, with 2 to the n queries, we can try every input and make a big table of them and then just figure out the property. Okay? So there's no kind of uncomputability issue here. There's definitely going to be something, and the maximum value is going to be the number of possible inputs. But that can be quite large, right, even when n is relatively small. And so we're interested in problems that might potentially have a query complexity that's much lower than 2 to the n. OK? And so, so the thing here, OK, let me give an example, and then I'll say that. So I already gave one example, actually, but I want to give another example, which I'm going to do in a little more detail. And so this is going to be a promise problem. And so what that means in the context of oracles is that there's a constraint on the oracle. The oracle is not some arbitrary function. It's a function that has a certain property. And the promise is that the oracle is either constant so O of x equals O of y for all inputs, or it's balanced, which means that the number of inputs such that O of x is equal to 1 is the same as the number of inputs, I'll call those y, such that O of y is equal to 0. OK? So does everyone understand what this promise is? OK? And then the property that we want to figure out, you might be able to guess, is which one it is. And just to be clear, I want to do this with 100% probability. So, so given that I want to be 100% sure that I got it right, then thinking about it a little bit, you can see that I'm going to have to try 2 to the n minus 1 plus 1 queries. So why is that? Well, if I try just 2 to the n minus 1 possible inputs, it could be that I got really unlucky in picking them, and they happen to be things that all had. So balanced means that these two sets are the same size, which means that they're both size 2 to the n minus 1, right? Because there's 2 to the n possible inputs. And so it could be that if I pick 2 to the n things, I just happen to always pick in the set, just out of bad luck. OK? But if I pick 2 to the n minus 1 plus 1 inputs, then I know that if it's balanced, I'll always get one from the other set. OK? And so if I get them that they're all the same, I know that it's constant then. Obviously, if I pick 2 possible inputs and they're different, then I know from the start that it's not constant. So I could get lucky right from the start. In fact, a randomized algorithm, probabilistic algorithm for this problem is like log of 2 to the n. So it's like n queries because, well, OK, it depends what probability you want to get. It's constant if you want to get constant probability, right? Because you pick a few of them, and each one has a 50% chance of being in one set or the other if it's balanced. So after 3, 4, 5, if you always get the same answer, it's starting to look likely that is constant. But you can never get to 100% probability that way unless you go all the way to this many queries. OK? So this should give you an example of the type of problem that we try to answer with oracle analysis. So a couple of comments here. So first of all, when we talk about query complexity, I only care about how many times I have to ask the oracle something. The gate complexity does not figure into this at all. So obviously, if we're querying the oracle some number of times, we need enough gates to kind of use all of those inputs, or all of those different queries that we tried. So the gate complexity is not going to be lower than the query complexity. But it could, in principle, be much higher. Right? It could be that we try these oracle queries, and then we have to calculate something really, really hard, or even uncomputable, right? Although it's finite size, so I guess there's nothing uncomputable. But it could be very, very hard. But nevertheless, this is kind of a useful model for real algorithms that don't have a black box. And why is that? Well, a lot of problems can be phrased in this way, where you have some function here, and you're trying to compute some that's relatively easy to compute. So you have a polynomial time algorithm to compute this oracle. And then we want to get some property of that function. We want to figure out some property of that function. And I'll be a little more explicit later about how that could work. And so if that's the case, if you have an oracle algorithm to solve the problem, then you can immediately plug in this kind of polynomial realization of the oracle. And that gives you an algorithm to solve the non-oracle version of the problem. Now, of course, if the gate complexity of your query algorithm is very large, that's not actually a useful algorithm. But frequently, the gate complexity is not that large. It's comparable to the number of queries. And so this can be a useful heuristic for finding algorithms. Solve this oracle problem, and then apply it to a real problem that can be modeled as that oracle problem. Yeah, OK. You had a question?
Yeah, I can answer.
OK. So yeah, and so the third thing, and the real reason that people started studying these oracle problems, I mean, that's one of the reasons that it can be useful for finding regular algorithms. But the other is that in this oracle model, it's actually possible to prove lower bounds, right? And I mean, I didn't really prove this to you, but I kind of gave you the idea. And certainly, it can be proved that this actually, truly, in a mathematically rigorous sense, is the number of queries you need to solve this problem. OK? And so originally, when people came up with this sort of analysis, the hope was that you could prove lower bounds on the oracle problems, and then somehow convert that to proving a lower bound on the non-oracle problems, and thereby prove, say, that P is not equal to NP, for instance. And this turns out not to work. That there's plenty of cases where you can prove a bound on the oracle problem, but then it just doesn't work for a bound on the other problem. It's not just you can't find a way, but you can actually make up oracles that will, you can have oracles that kind of model something and that you can prove in either direction. So specifically speaking, you can come up with complexity classes if you have access to a certain oracle. And then you say, well, if I have access to this oracle, now you're in this kind of oracle world, and you can prove some bounds. And you might be able to prove that with access to this oracle, P is not equal to NP. And people have done that. But then you can also come up with a different oracle. And you say, well, if I have access to this oracle, then P is equal to NP. OK? And the problem is that any kind of lower bound you prove on oracles is what's called relativizing, and that it still should work if you have access to some additional oracles. Because when you're querying the oracle, you're kind of just getting information about what's going on in there. And there's no other structure that you can take advantage other than what's given to you in the promise. And so having additional oracles around is not going to change that. But when you're talking about real complexity, it does matter. And in particular, if you kind of know more about the structure of this oracle, then you can potentially take advantage of that to do better. So for instance, in this particular case, suppose we know that the oracle function O of x is actually computed in this simple way. That we take one bit of the input, xi, and then the oracle is a xi plus b for some constants a and b. We don't know what I is, we don't know what a is, we don't know what b is, but we know it has this form. So you might say, OK, well, since we don't know what all those things are, we might as well model it as an oracle like this, right? It is true that for half of the inputs, that if a is 0, this is a constant. And if a is 1, then for half of the inputs, we get 0, and half of the inputs, we get 1. So it does satisfy this property. And so we might try to abstract it as this oracle. And indeed, any oracle that solves this problem will solve it for this particular case. But there's a much faster algorithm to solve it for this particular case, which is you try inputs with different values for this bit. So suppose you try the input 1, 0, 0, 0, 0. We'll try, first of all zeros, and then 1, 0, 0, 0, 0. OK? So if this bit is 1, then you'll see if A is 0, then it doesn't matter what we put in. We'll always get the same constant. We'll get B. But if A is 1 and I is 1, then trying those two inputs will reveal that they're different. Right? And similarly, if we try 0, 1, 0, 0, 0, and I is 2, we'll see that they're different. And 0, 0, 1, 0, 0, 0, if I is 3, we'll see that they're different. Okay? And so just by trying n plus 1 inputs, where we try the 1 in n different places and compare to the all zeros, if A is 1, we'll always find that out. Okay? So with 100% probability, we'll answer this with only n plus 1 queries rather than 2 to the n minus 1 plus 1 queries. Okay? So it's a huge difference. And that's the bottom line why this doesn't work for proving lower bounds. It can maybe give you some hint. You say, well, I don't think this function has any more structure that I can exploit, so I should model it by an oracle. But maybe there is some hidden structure there that you don't know about. And ultimately, that's why these oracle bounds can only be suggestive and not really prove anything about the unrelativized case. OK? So are there questions about that? OK, so then let's move on to quantum oracles. And so usually when people talk about quantum oracles, they're actually, I mean, a quantum oracle in principle could be some kind of black box unitary that just maps the state from one state to another. But usually people restrict attention, not always, but usually restrict attention to quantum oracles, which are some fairly obvious quantum analogs of the classical oracles. And in particular, we're going to make that kind of oracle reversible, and then we're going to put kets around it. So our oracle is going to be some unitary that, so this thing here is n qubits, and this is 1. And it's going to output x and a plus O of x, where O of x is the classical output for this oracle. So this is the quantum version of that classical oracle I had on the other board. OK? And so we might draw that like this, where we have a bunch of inputs here, and we have an ancilla, which starts as A. And then here we calculate O and use it to flip A or not. OK? And of course, the fact that this is a quantum circuit means that we could also do it not just on single inputs here, but on superpositions of inputs. And that's going to be the thing that's interesting that makes quantum oracles, in some cases, more interesting, more powerful. Well, more powerful is maybe not the right word. That we can run some more interesting quantum algorithms to reduce the query complexity in quantum oracles. OK? OK, so in particular, I'm going to try to find a quantum algorithm to solve this problem, the constant versus balanced problem. This is called the Deutsch-Jose algorithm. And this was basically one of the first quantum algorithms that kind of showed a quantum advantage, showed that you could do quantum things better than classical. OK, so we're going to start with n qubits here, all 0. And we're going to have one ancilla qubit. I guess I'll also start as 0. And then what we're going to do is we're going to do the Hadamard on each of these qubits. And then we apply this oracle. And now I want to do a z here. And then I'm going to do the oracle again. And then I'm going to Hadamard these again. And now I'm going to measure all of these qubits. And if this is all 0, the measurements are all 0, then I output constant. And if not, then I'm going to output balanced. OK, so let me divide this up into steps, and then we're going to go through step by step to understand what's going on. OK, so everyone remembers circuit diagrams, I hope, and so this picture at least makes sense. It may not, and probably doesn't make sense as to why I chose this particular sequence of things. That's what we're going to do now. But I just want to make sure you know what I'm drawing here. OK. OK, so what happens? Step 1 is straightforward. We just have the states all zeros. So that's our initial state. So what happens after step 2? Well, we do the Hadamard on each of the first n qubits. And so Hadamard takes 0 to 0 plus 1. And when we take the tensor product of 0 plus 1 over n qubits, well, we can have any bit string. Right? And this was an equal superposition of all possible bit strings. So we can write that as sum over x, x, 0. And then step 3, now we're doing the oracle. So we're interacting the oracle on the first n bits, which could be any x, with this ancilla. And so we have sum over x, x, and then O of x. And then in step 4, we're going to do a z on this ancilla qubit. So that gives a phase of +1 if O of x is 0, and a phase of -1 if O of x is 1. Here, let me put the -1 here. So it's sorry, -1 to the O of x here. And then x O of x. OK? And then step 5, we do the oracle again. And so what does that do? Well, it adds to this thing O of x, which will cancel it out always. So we have the state sum x -1 to the O of x, x, and then 0. OK? So basically what we've done here is we made a superposition of all possible inputs. We calculated O of x with a query. And then we did a phase shift depending on the outcome of that. And then we uncomputed this oracle. And so now what happens next, let's break up into two cases. One is the constant case, and one is the balanced case. So let's do constant first. So if the function is constant, then O of x is either always 0 or it's always 1. And so this phase here doesn't depend on x. It's just a global phase. So if it's constant, then the state after 5 is plus or minus sum over x, x, 0. Right? Yeah.
Sorry, kind of a trivial question, but why does applying O twice give it 0? Or?
Oh, yeah. So remember what the oracle, the quantum version of the oracle does. We made it kind of like the reversible computation. We're adding O of x to the second and so on. So this is O of x plus O of x, right. But we're working mod 2.
Oh, I see.
So that's 0. OK, so if it's constant, this phase comes out front. We just have sum over x of x. And at step 6, when we do the Hadamard transform on everything, well, remember that Hadamard is its own inverse. And it took all zeros to sum over x of x, sum over all possible x's. So if we do the Hadamard again on this, we'll get back all zeros. And then, of course, step 7, we get the output all zeros here. And so step 8, we'll say constant, as we should. OK? Did that make sense? OK. So what happens if it's balanced? So that's a little bit more complicated. So for balanced, at step 5, well, since it's balanced, we know that there's 2 to the n minus 1 inputs that give us plus 1, and 2 to the n minus inputs that give us minus 1. So this thing here is a superposition over all possible x's, but some of them, half of them, have the phase plus 1, and half of them have the phase minus 1. So here let's let phi equal the state that we actually have here. And now I want to let psi be this state, sum over x of x, which is what we get in the constant case, or what we get from Hadamarding all zeros. So notice this thing has 2 to the n plus signs. This has half plus and half minus. And so what that means is if you take the inner product, psi and phi, it's 0. Right? And so in step 6, when we take the Hadamard of phi, and I guess we have 0 on the ancilla, the Hadamard of phi has to also be orthogonal to the Hadamard of psi. Right? Because these two things cancel. And the Hadamard of psi is the all zero state. Okay, so whatever state we're getting here at step 6, we know it's orthogonal to the all zero state. And so that means that whatever we get here, whatever bit string we get here, is not equal to the all zero state. It could be basically it could be anything else, but it's definitely not all zeros. Okay, and so that means that at step 8 we're getting something that's not all zeros, and so we'll output balanced, which is correct. Okay? So did everyone follow that? Are there any questions on this algorithm? Oh, maybe I didn't. Maybe I should say what the bottom line is. So this is a quantum algorithm. It used 2 queries to the oracle, but it solves this problem with 100% probability. So that's a big difference from the classical case, right? The classical case used 2 to the n minus 1 plus 1 queries. Here we're doing it with just 2 queries. Okay? So this is what I mean when I say this is an algorithm that shows a big quantum advantage.
So what are the 2 queries here? It's if it's constant or balance, is that? Or?
Yeah, so the queries.
Yeah. Okay.
The queries are here, steps 3 and step 5.
Okay.
Those are the only things that use the oracle. Everything else is just gates, right? And so we don't count those towards the query complexity. But every time we apply the oracle, that we have to count.
So I didn't follow when you went from the second line to the third line on the right side.
Sorry, here?
Yeah.
Oh, OK. So, so what I'm doing here is I'm taking the inner product of the state phi after the Hadamard with the state psi after the Hadamard. And because the Hadamard, well, I mean, it's just because it's unitary, actually. There should be daggers here, but that doesn't matter. These things cancel, so we can do that, and it stays the same. And it's just the point is that doing a unitary doesn't change the relative inner product of states. That's kind of the definition of what unitary is. OK? So are there other questions about this?
Why were psi and phi orthogonal in the first place?
Oh, right. Because phi, remember, it's a balanced function. So phi has an equal number of, it's still a superposition of all x's, but it's an equal number of pluses and minuses, right? And so when you calculate this inner product, every time you get a plus, you get a plus, and every time you get a minus, you get a minus. And so you have 2 to the n minus 1 pluses and 2 to the n minus 1 minuses. So they cancel out. Any other questions? Yeah.
Question: when you move from step 2 to step 3, so there, like, you use the oracle 2 to the n times, right?
No, I'm using it 1 time, right? So that's what the quantum oracle does.
Yeah, but like,
right? It calculates on a single input. It calculates that. But if I apply it to a superposition, it still has to work, right? And this is what it does. So when I'm applying it to a superposition, it's not applying it 2 to the n times. It's applying it 1 time. And that's kind of the special nature of quantum mechanics. Just in the same way that I have a superposition that, I mean, that when I do this z gate in step 3, I'm only applying 1 z gate to a single qubit, even though I have a superposition of 2 to the n things. Sorry, step 4, I guess that was. OK? So one more thing I want to point out about this algorithm. So I use this oracle twice. So why did I use it twice? So what happens if I had not used that second thing? If I had not uncomputed the oracle? So if I hadn't done this in step 5, well, now I have a different state here. This is an entangled state between the main part, the n qubits, and the ancilla qubit. And now you could imagine, in fact, so in this case, I'm just kind of discarding that ancilla qubit because I'm not using it again. It's reset to 0. But suppose I had measured it instead. And that wouldn't make any difference to what happens to the other n qubits, right? Because you could move it very far away and measure it, and you never know whether you actually measured it or not. So suppose you measured it and got to state 0. Well, so in the constant case, that would mean that all the inputs gave 0. And so we have superposition of all x's. In the balanced case, well, we'd have a superposition only of half the x's, right? The ones that gave 0. But those 2 states are not orthogonal anymore, right? They have an inner product of, I guess, 1 over root 2. And so this argument doesn't work anymore. Instead of never getting all zeros, we would get all zeros half the time. And that means the algorithm would not work 100% of the time. It would still work half the time. But we want it 100%, right? Classically, you can already do very well probabilistically. And so that's a concrete example of why you need to do this uncomputing of scratch bits that I mentioned last week. Okay? This algorithm depends on your being able to do that. Yeah. Sorry, that's not a question. Just, sorry. Too eager to answer questions. OK. So let's see. So you have, I guess, the tutorial today. And so you're going to do some more stuff with this algorithm. It turns out that you don't actually need 2 oracle calls, despite what I just said. There's a trick that you can get it down to 1 oracle call, and that's one of the tutorial problems. And there's also the third problem is about Euclid's algorithm, which is kind of going to be a warm-up for what we're going to be doing tomorrow and maybe Thursday with Shor's algorithm. Shor's algorithm is for factoring large numbers, and so we have to be able to do stuff, kind of number theory stuff, in order to make that work. And so this Euclid's algorithm is a classical algorithm in both the sense that it runs on classical computers and that it dates back to ancient Greece. So yeah, hopefully you can figure that out. And like I said, tomorrow we're going to be going to factoring.